Okay, we're going to resume our discussion on enthalpy. We want to tie these thermochemical equations into stoichiometry. So we know what a thermochemical equation is. We know how to do stoichiometry with plain old chemical equations. Why not add this little bit of information and utilize it in our in doing stoichiometry? Okay, so before we do that, I want to just kind of, for a little bit, revisit the first law of thermodynamics. If you look at that equation, we haven't seen that equation before. Let's see if we can imagine where it came from. Here is our mathematical representation of the first law of thermodynamics. If you do this reaction under a constant pressure environment, what does Q become? Well, it becomes delta H. They are synonymous as long as it's a constant pressure environment. If a gas is expanding against a constant pressure, then we have our work term. And what does work equal? Well, it equals a negative P delta V. So if we combine those together, we have this equation that we see there. Now, sometimes you'll see this equation kind of with the delta H on the left-hand side and the delta E on the right-hand side, and that would be fine as well. But this is the first law of thermodynamics with our information that we know about Q and W applied. Okay, so if in the course of doing a reaction there are no net change in moles of gas, maybe you had 2 moles of gas to begin with and the reaction took place and you still have 2 moles of gas, or you started off with all solids and you still have all solids. If there is no change in the number of moles of gas, then it's not going to be changing the volume. It is not going to be expanding. It is not going to be contracting. So if that is true, what could we say that delta E equals? Well, if that were true, then delta E and delta H are numerically the same thing. And so many reactions that's true. And a lot of times we'll say change in energy when we're talking about delta H, for that very reason, because delta H and delta E are very often the same magnitude. But the fact of the matter is, even if a reaction is taking place and the work term is changing, if you do have an expansion of a gas or a contraction of gas by making more moles of gas or consuming the moles of the gas during the course of the reaction, this term is typically much smaller than the heat transfer part. And so those are very similar in magnitude, even if there is a gas involved. And so, like I said, once again, very often you'll hear me say change in energy when we're sitting here staring at a delta H, because the change in internal energy and the change in delta H are either the same or they're very close to being the same. So we could take PV equals nRT, and up there at that top equation where we see a P delta V, we could do some substitution. PV equals nRT. We see the PV. What gives us a change in V? What gives us a change in V is a change in N, the change in number of moles. So it becomes this equation right here. And I'll just put a little box around it here. This equation is the top equation that we see up there. But instead of the P and the V, we have nRT, change in N, which is leading to that change in volume. So we're just tying things together that we've learned along the way, things that we learned in Chapter 5, tying into our information of a gas expanding during the course of a reaction or contracting during the course of a reaction. So then we could take an equation like this, where we do know the delta H, and we could calculate the delta E when this reaction takes place. Now, as we look at this reaction here, we see that we're starting off with some gas and we are producing some gas. At first glance, we might not notice this fact, but let's figure it out. What is the change in the number of moles of gas? That's the only thing we care about, because that's going to be an expansion or a contraction. Well, how many moles of gas do we have on the right-hand side of this equation? We have 3 moles of gas on the right-hand side. How many moles of gas do we have on the left-hand side? We have 3 moles of gas on the left-hand side. So are we changing how much gas is there? So what do we know about the work term? There's no expansion, there's no contraction, so the delta E is equal to the delta H, and that is equal to negative 890.4 kilojoules. But let's pretend. All right, are we ready to pretend? Let's pretend that this reaction, and I'm going to go over on the screen and write a change, a very little change. Let's pretend that we're not making a gas, but we're making liquid water. It's not gaseous water, but liquid water. Okay, now we can come back to the light board and see how that would change things. Would the delta N equal to be 0 now? No. We are finishing with 1 mole of gas, just the carbon dioxide, where we started with 3 moles of gas, and so our delta N is a -2. So now the delta E is equal to the delta H, okay, and we can have that second term minus RT delta N. All right, so let's plug numbers in for this, and for our delta H for that matter. So we have our negative 890.4 kilojoules here, minus R. We got a couple choices of R. We have one that has liter atmosphere per mole Kelvin, and we have one that's joule per mole Kelvin. We can look at our periodic table and see those values given to us there. And I'm going to choose the one that's 8.314 joules per mole Kelvin. Well, that's still not going to do very good of adding with my, and let me back away from here just a little bit, with my kilojoules. So let's go ahead and take that R and get it in kilojoules instead. So I don't want joules, I want kilojoules, and I would divide it by 1,000. So there's my R. They'd have to tell me what temperature this reaction is running in, and in our pretend, in the first part it didn't matter, but now that we have a pretend world, let's do our pretend, and I'm going to tell you that the temperature is 298 Kelvin. Okay, so I would have had to add that to the problem if we were going to work it. So we'll put 298 Kelvin. And we'll put our change in moles in there, which we determined was a -2 for our change in moles. And let me go ahead and write mole. And then everything's going to cancel except for kilojoules here and kilojoules here. And I'm not going to finish that one off. But if we finish that one off, because we're pretending, and I'm pretending on the fly here, but we could then add these terms, because that negative and that negative would make this a positive. It's going to add a little bit of energy. As it contracts, it's doing work on the system, so that is a positive work. It's going to be a little less negative, but not much less negative than this value that we see right here. Okay, so let's continue to examine this equation, okay? We looked at this one earlier and we did some manipulations with it, okay? What it wants to know here in this problem is when 1 mole of carbon dioxide is produced, what's the enthalpy change? Well, look at that balanced equation. That balanced equation says I'm making 1 mole of carbon dioxide. So if I'm making 1 mole of carbon dioxide, the amount of enthalpy change is going to be what we see in that thermochemical equation, -890.4 kilojoules. But what if we were going to make or consume, okay, 2.5 moles of oxygen? Now, if it was 2 moles of oxygen, the balanced equation is as we see it. 2 moles of oxygen consumed would make a -890.4. But this is not 2 moles, this is 2.5 moles. All right, and they wanted to know the enthalpy change when this reaction took place, but I had more oxygen, and more oxygen reacted, so there was more methane, and there was more carbon dioxide produced, and more water produced. So how would we do this? To do this, we're going to learn how to incorporate our delta H into dimensional analysis so that we can do it with stoichiometry. This is how it looks, okay? So we didn't have 2.0, we had 2.5 moles of oxygen. I didn't want moles of oxygen, I wanted kilojoules. So what I do is I go to my balanced thermochemical equation and I'm getting these numbers. Where do those numbers come from? Well, the bottom number is the coefficient in the balanced equation. The balanced equation said every time 2 moles of oxygen reacts, I get this much energy. So that's where this is coming from, okay? This is a new unit factor, a new dimensional analysis piece that we can add in our equation, and we can utilize it when we're doing stoichiometry to figure out how much related to how much energy, how much substance versus how much energy is given off or absorbed. Okay, so it's a new conversion tool. It's a new leg on our stoichiometry map. So let's look at our map, okay? Oh, well, let's put a big red box around this first, okay? This new conversion tool is going to be an important tool for us to use in the rest of this chapter dealing with thermochemistry. Okay, so where did I put this, okay? It's kind of getting crowded in here. We already had the, when we dealt with solutions, we dealt with that conversion, okay? And we went from liters to moles. When we were dealing with gases, we had this PVT boulevard. Now we're dealing with thermochemical equations, and we have a way to get from energy into moles, okay? Or if we knew moles, we could get out to energy. But the balanced thermochemical equation is what utilizes that, and I did not give it a good, clever name. You can come up with your own clever name for that road if you like and put it in your map. So here is a problem, okay? Now I want to see if you can tie these guys together. Can you tie them together and come up with which one of those answers is the best answer for how much energy would be produced, okay? What would be the delta H if 1.26 times 10 to the 4th grams of ammonia were produced? Pause the video, and when you've got an answer, resume. All right, so hopefully you tried one of these and you came up with answer C. I don't have a star popping up there, but C is the correct answer. So if you got C, you're great. If you picked A, you forgot to use the 2 that's in front of NH3. You see that 2 coefficient? You forgot to use it when you were doing conversions. So that's one of those wrong answers that I am quite certain, because it's twice as big as what it should be. If you got the answer and you feel real good about how you use dimensional analysis to come up with your answer in the thermochemical equation, then you are finished with this lesson. Otherwise, you might want to stay tuned, and I'll work through this problem and show you how it goes. So they're giving you some information. What are they giving you? They're giving you that you have 1.26 times 10 to the 4th grams of ammonia. That's what you were given. Now you're given a balanced thermochemical equation, and it gives you a relationship between moles of ammonia and energy. Now it gives you a relationship between moles of a nitrogen and energy, moles of hydrogen and energy, but we don't care about those. We care about the ammonia. So I'm going to go from the grams of ammonia to the moles of ammonia. And I'm going to go to the periodic table and take 1 nitrogen and 3 hydrogens, and that's going to give me 17.0, let's see what it is, 034 grams in a mole, okay? And now I don't just have grams of ammonia, but I have moles of ammonia, and now I'm ready to use the thermochemical equation portion. I can go from moles of ammonia to kilojoules. And the balanced equation says that every time 2 moles of ammonia are produced, you're going to generate or give off 92.6 kilojoules of heat. So that gives us a delta H for this amount, okay? And I don't want to call it a delta H. Let's just say the heat given off for this amount is going to be that negative 3.42, and the units will be in kilojoules. It's in the 4th. Okay, that's what you're going to get. So I know that if you forgot that little 2 there, or you forgot to utilize that little 2 there, that's going to give you answer A. And but that is how you use this term. You use this term by first getting to moles, and then you can use it to determine the amount of energy. So this is what we would say. When 1.26 times 10 to the 4th grams of ammonia react, okay, we will give off a negative 3.42 times 10 to the 4th kilojoules of heat. Notice how I use the language. We will give off this much heat. We won't say we will give off a negative 3.42, though I wouldn't give that as 2 choices on test. How much heat would you give off? And give a positive number and a negative number. It would be more accurate to say you give off 3.42 times 10 to the 4th kilojoules of heat, or say the change in heat or the change in enthalpy is a negative 3.42 times 10 to the 4th kilojoules. If you did this reaction under a constant pressure environment, this would be the change in enthalpy of that reaction, which would be synonymous with the heat transferred in that chemical reaction. Okay, so what we're going to be going into next is determining delta H for reaction. I've given you thermochemical equations and we've been handed delta H's, but there's basically 4 ways to calculate the delta H for reaction. The first way is with something called calorimetry. Okay, now my discussion of delta H was section 6.5 in your book, and so I jumped ahead to that, and then we will back up to 6.5 and 6.7. That's calorimetry, and that's the experimental way of determining the delta H of a reaction. It's the most challenging of the ways. We will see that you'll make measurements of heat, of temperature change, and be able to determine the delta H of a reaction. The second way is using Hess's law. We'll cover that in 6.8. The third way is called using something called heats of formation. These are values that are tables full of heats of formation. We'll learn how to utilize those. And then we won't look at this right now. We'll wait for much later. We can estimate delta H for a reaction, use something called bond dissociation energies. But we have to learn about what are called Lewis structures before we can do that, and that's not until chapter 9. So these are the 4 common ways, and I'll just reiterate. Number 1 is the most challenging, so bear with us as we really work through doing that. And then the second and third way we'll talk about in this chapter later on.